Hello everyone. In this module, our main focus would be to get back to structural coverage criteria on graphs that we saw 2 modules ago and look at algorithms that will help us to write down the test requirements for each of the coverage criteria that we saw, and also look at algorithms that will help us to generate test paths that will meet the test requirements for these algorithms. So just to recap the overall module that we are looking at currently, we are now looking at designing test cases where software artifacts are modeled as graphs. So in the graph models, we consider two kinds of coverage criteria. Coverage criteria based on the structures of the graph, which we saw 2 modules ago. And in the next week, we will look at coverage criteria on graphs augmented with variables, data talking about variables, and see data flow coverage criteria. Moving on from there, we'll see how various software artifacts can be modeled as these graphs and how these coverage criteria can be used for designing test cases. Now, what will be the focus of this lecture? We look at algorithms for structural coverage criteria in this lecture. So to recap, what was the structural coverage criteria over graphs that we saw about 2 lectures ago? So if you remember, we saw all these coverage criteria. We began with node or vertex coverage. Then we moved on to edge coverage. We looked at edge pair coverage. And then we looked at path coverage in graphs. We began with complete path coverage, which I told you was infeasible if a graph has a single loop or a self loop, because you can go round and round the loop several times and get infinite number of paths. So there's no notion of a finite path set that I can completely cover. So a workaround would be to do specified path coverage. Specified path coverage is where a user gives the paths. Another interesting path coverage criteria that has existed in the testing literature is that of prime paths coverage. These especially help to cover graphs with loops by helping us to execute the loop once, execute the loop many times, and also to skip the loop. And then prime paths that begin and end with the same node are what are called round trip coverage. So we ended the structural coverage criteria lecture by looking at 2 round-trip coverage criteria. One was complete round-trip coverage, which insisted that you cover all the round trips. The next one was simple round-trip coverage, which insisted that you cover one of the round trips. So what we will be looking at now is, fine, we have these coverage criteria. Each coverage criteria has a set of test requirements as per the criteria that is under consideration. And then our goal as a tester is to be able to define test paths for those coverage criteria, right? How does one go about doing it, right? So what are the algorithms that will help us to do this, right? So we saw DFS and BFS. Now we will see how to use these algorithms to be able to define algorithms for these coverage criteria. So when I talk about coverage criteria that I discussed in this slide, for each of those coverage criteria, we basically saw 2 entities, right? So one entity was what is called a test requirement. So when I say you achieve edge pair coverage, the test requirement is achieving edge pair coverage. Corresponding to this test requirement, I look at the graph and generate a set of test paths in the graph that will achieve this test requirement for edge pair coverage. So when I talk about coverage criteria, I'm talking about 2 entities that are related to the coverage criteria. One is the criteria specified as a test requirement, abbreviated as TR, and the other is a set of test paths which occur as test case that are designed to satisfy that criteria. Now, it could very well be the case that the criteria that I define is infeasible. Like I told you, right? If there is a graph that has a loop and my criteria says do complete path coverage, it's directly infeasible because there are an infinite number of paths. So only for feasible coverage criteria as test requirements do we talk about designing test paths as test cases for them. For infeasible coverage criteria, we don't even consider test paths. So another interesting problem, if you step back and ask, you could ask yourself, Am I considering the problem of deciding whether a given coverage criteria is feasible or not? Yes, this is a very important problem, but that will not be the focus of this course because, as I told you, it is an undecidable problem to check whether several different coverage criteria are feasible or not. And because this course is intended to be an application oriented course, I really don't want to introduce how you get those undecidability results and what are the reduction proofs and all that. So what we will focus is, we'll assume that the test criteria that we are working with are feasible, and then we'll see how to write test requirements for them and how to design test cases as test paths for them. We'll begin with this listing, one at a time we'll look at. So we begin with node and vertex coverage and then we'll move on around this list, right? So we begin with node and edge coverage. As I told you, for each of these coverage criteria, two things to look at. What is the test requirement or TR, and what is the test case that will satisfy those TRs. What are test cases? Test cases are test paths in the graph that will satisfy the test requirement. Just to recap, a test path always has to begin at a designated initial node and end in one of the designated final nodes. That's one of the requirements that we imposed as a part of the definition of test paths in this course, right? So for node and edge coverage, the test requirements are already given along with the graph, right? What is the test requirement for node coverage? It is basically the set of all nodes of the graph, the set of all vertices of the graph. What is the test requirement for edge coverage? It is basically the set of all edges of the graph. There's nothing much to do, right? Now, these are the TRs. They're already given to you. We don't need any algorithms to list them or define them specifically. Now, what about test cases or test paths that will satisfy node coverage or edge coverage? If you see, for node coverage, very simple application of breadth first search that we saw about one lecture ago will directly give us node coverage, right? Or even depth first search. You take a graph, fix a source node and do BFS or DFS on that node. It will result in a breadth first tree or a depth first tree of the graph. Suppose this tree spans out all the graphs. There it is. The paths of this tree will give you the test paths as test cases for node coverage. Suppose the first breadth first search or the first DFS doesn't finish exploring all the vertices of the graph. There are vertices that were not reachable from this designated source. Then you fix a new source and start DFS or BFS again from that source and you get another tree. So this way you run DFS or BFS on the complete graph till you get forest of trees, and the resulting forest of trees will give you the set of test paths that will achieve node coverage. You can do a very similar thing for edge coverage, right? I can do a simple modification of the BFS algorithm wherein after running BFS algorithm, I check if I have indeed covered all the edges of the graph, and if I haven't covered all the edges of the graph, I consider the remaining edges, which could be cross edges, tree edges or back edges, and see how I can include them in the test paths to be able to obtain test paths that act as test cases for node and edge coverage. Just one additional point here, it would be useful to begin your search from the designated initial node in the graph, right? Because that is where ideally a test path will originate. And if you begin your BFS or DFS from the initial node, you directly have a test path that will end in one of the final nodes. In case the path doesn't end in one of the final nodes, you could see how to extend it to the final node in case the final node is reachable. If the final node is not reachable from the initial node, then you have to begin somewhere else in another fresh source for DFS or BFS, right? We move on. Now the next coverage criteria in our list is what is called edge pair coverage. The test requirement for edge pair coverage is all paths of length 2. Right? So here when I say all paths of length 2, I need to include paths that involve self loops also. How do I compute all paths of length 2? I can compute all paths of length 2 by exploring the adjacency list of a node and its successor and stopping at that, right? Exploring the adjacency list of one node will give me the edges that are adjacent to that node, that are incident on that node, and exploring the adjacency list of each of these successors would give me the edges that are incident to each of these successors. This would give me a path of length 2, and that is what is needed for edge pair coverage. Once I have the TR for edge pair coverage, the test requirement itself could act as a test path. We saw an example of a graph where in fact we cannot do better than that. The TR itself becomes the test path. Otherwise, what I do is I can again run BFS or DFS and get a set of test paths that will satisfy edge pair coverage as a test requirement. Now, the next coverage criterion in our list is what is called complete path coverage. As I told you, complete path coverage is many times not feasible. It's not feasible in graphs that have loops, and graphs that model software artifacts do have loops. Typically, control flow graphs do have loops. So there is no point in looking at complete path coverage, because it will be infeasible. So we directly move on and look at prime path coverage. So just to recap, what is a prime path? Prime paths are maximal simple paths. That is, they are simple paths that don't come as subpaths of any other simple paths, right? So now I want to be able to do the same old two things for prime paths. I want to be able to define TR, test requirement for prime path. After I finish doing that, I want to be able to define test cases that will meet this test requirement for this prime path. To begin with, we look at test requirements for prime path and what are the algorithms to see that. So instead of giving you the pseudocode for the algorithm like we did for BFS and DFS, what I thought we could do is we could take an example graph and I'll walk you through how the algorithm will run to compute the list of prime paths. So once the algorithm computes the list of prime paths, what I have with me is basically still my test requirements. With this list of prime paths as my test requirement, I now have to go ahead and generate test paths that will cover or satisfy all these prime paths, right? So I'll walk you through an example and explain the algorithm by using that example. So here is a simple graph. Here it has 7 nodes beginning from 0 and ending at 6. 0 is an initial node, 6 is a final node as it's marked with a double circle. This graph has branching. It has branching at node 1. It branches into 5 or 2. This graph also has a self loop here at node 4. And this graph has a cycle here. 1, 2, 3, 1. This is a cycle, right? So it will be interesting to look at prime paths. As I told you, what is the single big use of prime paths? Assuming that this cycle represents a loop, prime paths give you a neat coverage criteria that will help you to cover this loop. It will help you to skip the loop. It will help you to execute the loop on its normal operations, right? So you can assume that there are 2 loops, one self loop here and one cycle here. So we'll see how to compute prime paths for this graph as a test requirement first, and then we will see test cases that will help us to achieve this test requirement, right? So what are prime paths? Prime paths are maximal simple paths. So what is the strategy that my algorithm will follow is the following. So what it will do is that it will take this graph and it will enumerate all simple paths one after the other. So is there a systematic way of enumerating simple paths? Yes, the following is the systematic way of enumerating simple paths that we will follow. So we'll enumerate simple paths in order of increasing length. That is, we'll enumerate simple paths of length 0. Then we'll enumerate simple paths of length 1. We'll enumerate simple paths of length 2 and so on. And then when do we end? What is the criteria to end? Please note that we are enumerating simple paths, right? So what is the maximum length that a simple path in a given graph can have? Because simple paths cannot contain cycle, the maximum length that a simple path in a given graph can have is the number of vertices, right? So our algorithm is guaranteed to stop, right? So what we do to begin with, we enumerate simple paths of increasing length, and as and when we enumerate simple paths of increasing length, we will mark out some of those paths as being prime paths and pull them out, right? As and when we mark and pull them out and finish enumerating all the simple paths, the final list of marked and pulled out simple paths will be the prime paths that we will obtain as a test requirement, right? So I'll show you how that works for this example graph. So I begin with enumerating simple paths of length 0, right? So what is a simple path of length 0? Simple path of length 0 is just the vertex, right? Because it has one single vertex. How many vertices are there in this graph? There are 7 vertices starting from 0, 1, 2, 3 and so on up to 6. So I enumerate each of these vertices as a path of length 0. There are 7 such paths of length 0. I've just enumerated them. Another thing to be noted is at the end of this 0 length simple path which contains this single vertex 6, I have put an exclamation mark. What is the role of the exclamation mark? The exclamation mark tells us that this path, this simple path which contains the single vertex 6, cannot be extended anymore as far as this graph is concerned. Why is that so? Because 6 is a final vertex and there are no edges that are going out of 6. Right? So as far as this graph is concerned, simple path 6 cannot be extended anymore. So I remember that by putting an exclamation mark. Right? So now after enumerating all paths of length 0, I go ahead and enumerate paths of length 1. So here is the same graph and here are the paths of length 1. How have I enumerated paths of length 1? I go back to the previous slide. So I say here is a path of length 0 which begins at vertex 0. Right? So you go back and look at the graph, vertex 0. Vertex 0, what are the two paths emerging from vertex 0? A path of length 1 from 0 to 4. A path of length 1 from 0 to 1. That's what I've written here. Vertex 0, this path of length 0 can be extended to two paths of length 1, namely the edge 0, 1 and the edge 0, 4. Similarly, vertex 1, which was a simple path of length 0, can be extended to two paths of length 1, paths 1, 2 and path 1, 5. If we move on, vertex 2 can be extended to path 2, 3. Vertex 3 can be extended to path 3, 1. Vertex 4 can be extended to two simple paths of length 1, one leading to 6 and one using the self loop from 4 to itself. And vertex 5 can be extended to one simple path of length 1, which is the edge 5, 6. Now let's look at what are these exclamation marks that we have put like last slide. So again, in this listing of paths of length 1, 9 simple paths, I have put two paths with exclamation mark, which means both the paths end in the final node 6 and they cannot be extended further. So exclamation mark for us is to mean that this path cannot be extended further. Why am I interested in paths that cannot be extended further? Paths that cannot be extended further could mean that they are heading towards being a maximal simple path. And that's my interest, right? Maximal simple paths or prime paths is what I want to look at. So in addition to exclamation mark, I have also gone ahead and put an asterisk here. What does that mean? That means the following. This means that this path, which is this edge 4 to 4, it cannot be extended further, not because there are no outgoing edges, but because it already forms a simple cycle. Remember, if the only way to extend it further is to use this edge once again, 4, 4 and 4, in which case it will not turn out to be a simple path, which is not interest to me. And the other way to do it is to do 4, 4 or 6, in which case also it will not be a simple path, so it's not of interest to me. So I mark it with the asterisk, which says that this path also cannot be extended further. Now I look at all the other remaining paths, which is this list on top, and see how to extend them to get simple paths of length 2. So you look at the path 0, 1. I extend the path 0, 1 into two possible paths of length 2, path going from 0 to 1 and then from 1 to 2, and path going from 0 to 1 and then from 1 to 5. That's what is listed here. Similarly, the path 0, 4 can be extended to 0, 4, 6. Please note that I can also extend 0, 4 to 0, 4 and 4. But that's not a simple path, so I don't list it here. Right? And I go on doing this. Path 1, 2 can be extended to 1, 2, 3. Path 1, 5 can be extended to 1, 5, 6, which comes with an exclamation mark because that's where it stops, can't be extended further. Similarly, path 2, 3 can be extended to 2, 3, 1. 3, 1 can be extended to 3, 1, 2 and 3, 1, 5. So paths of length 2, how many paths are there? 8 paths are there and 2 of them can't be extended further. Right? Now I start with paths of length 2 and consider paths of length 3. It so happens that I get 7 different paths. So path 0, 1, 2 can be extended to 0, 1, 2, 3. Path 0, 1, 5 can be extended to 0, 1, 5, 6, right? Path 1, 2, 3 can be extended to 1, 2, 3, 1. I can go back and so on, right? If you see in this listing, almost every path of length 3 is marked with an exclamation mark or an asterisk, right? In fact, there is exactly one path that is not marked with either of these. What do all these marked paths mean? They mean that that's it. We can't extend them anymore. We can't extend them anymore for two reasons. One is they end in a vertex from which there are no outgoing edges, or if we extend them further, I'll violate the criteria of they being a simple path. So I'm pretty much closed here as far as paths of length 3 are concerned. There's only one path here, 2, 3, 1, 5, that's not marked. So that's the only path that has scope for extension. So I go ahead, take that path and extend it by adding the edge 5, 6. You see, 2, 3, 1, 5 was the path of length 3. I can extend it to length 4 by adding this edge 5, 6. That's what I've done here. And the moment I did that, I am forced to put an exclamation mark here for the same reason, because I have ended in the node 6, which is a final node, and it doesn't have any outgoing edges, right? So what do I do? Here is the algorithm in English. I consider paths of length 2 by extending paths of length 1 with every node that can be reached from the final node in the path, unless that node is already in the path and is not the first node, right? And I keep doing this for paths of length n, increase to path of length n plus 1, till I reach path of length mod v. Why do I stop at mod v? Because that gives me the maximum length simple paths. Any other path of length greater than mod v, by pigeonhole principle, one vertex has to repeat and the path will not be simple anymore, right? So I hope the algorithm is clear. What does the algorithm do? It starts with paths of length 0, extends them to obtain paths of length 1, extends them to obtain paths of length 2, extends them to obtain paths of length 3, keeps repeating this till it can get paths of maximum length, which is the length as the number of vertices. While doing these extensions, it marks out certain paths. There are two kinds of markings that we do. We mark it with an exclamation mark or we mark it with an asterisk. When do we mark it with an exclamation mark? When I know that that particular path cannot be extended because there may not be any outgoing edges. I mark it with an asterisk when I know that if I extend it, I will violate the criteria that this path needs to be a simple path, right? All the other paths at every step that are not marked with one of these special markers can be extended, and I keep repeating this process, right? So for this particular graph, it so happens that there are 32 simple paths for this particular graph, but only 8 of them are prime paths, and those are the ones that have been obtained by these markings, right? In general, it's not an easy problem to count the number of simple paths. I've just given this for this specific graph. And why is this algorithm guaranteed to terminate? Because it is to stop when I get a path of length mod v, as we discussed, right? So now I'll just present this graph and all the prime paths for this graph. So this is the graph that we've been using to understand our algorithm. And here are all the prime paths that I worked my algorithm out and I've listed through that. So let's look at them. The path 4, 4, it's this, which was listed as a path of length 1, if you remember, and right then marked with a star because it couldn't be extended. It was already a simple cycle. Then there was a path 0, 4, 6, right? Then there's a path 0, 1, 2, 3, 0, 1, 5, 6, then 1, 2, 3, 1, 2, 3, 1, and then 2, 3, 1, 2, 3, 1, 2, 3, right? If you see these three paths, 1, 2, 3, 1, they basically correspond to this cycle in the graph, and between the three paths, they tell you various ways in which you could traverse this loop, right? And this path 4, 4 is a prime path that covers this loop. The rest of the paths traverse the rest of the graph. Like for example, the path 0, 1, 5, 6 skips this loop, right? The path 0, 4, 6 skips this loop, right? And then the other path that is left is 2, 3, 1, 5, 6. That is like exiting this loop 1, 2, 3 and coming out to a final node, right? So for this graph, our algorithm that begins by enumerating simple paths of increasing length and identifying prime paths as and when we enumerate them, ends by listing all these 8 paths as prime paths in the graph. And if you sort of play them back in the graph like we did just now, you can see how they neatly cover the 2 loops and how they skip the loop in the graph, right? So now what have we done? What we've done so far just gives us the test requirement or TR for prime path coverage. We say now you write a set of test cases for covering these paths. This elaborate exercise that we did was just to obtain the test requirement for prime path coverage. We still have to go ahead and design test cases to be able to get test paths to meet the test requirement for prime path coverage. How do we go ahead and get the test paths for prime path coverage? Again, there are several algorithms that have been used in literature. I'll give you one algorithm that I'll illustrate on the same example because that turns out to list the prime paths. It's a heuristic that lists it reasonably faster than other known algorithms. So what we do is in this list of prime paths, which are given as my test requirement, you start with the longest path. Which is the longest path in this list? That's this last path, 2, 3, 1, 5, 6. What you do is that you extend this path to the left to see if you can find a path from the initial node to the beginning node of this path. And then from the right, assuming that this is not a final node, you see if you can extend it to the right to make it end in a final node. In this case, 6 is already a final node. So I've already ended in the final node, but 2 is not an initial node. So I take this longest prime path and see if I can go to the left and extend this path to make it as if it was beginning from an initial node, right? So if I do that for 2, 3, 1, 5, 6, I get such a path. I get 0, 1, 2, 3, 1, 2, 3, 1, 5, 6, right? So I'll trace it out here, 0, 1, 2, 3, right? 1, 2, 3, 1, 5, 6. Now you might ask, why did I repeat this 1, 2, 3 twice? I repeated that with the purpose of, I could have not done that. I could have done 0, 1, 2, 3, 1, 5, 6. In which case, I would not have covered these paths here. If you remember, I had 3 prime paths which tell you how to traverse the loop beginning from 3 different vertices of the loop. I could begin the loop at 1, I could begin the loop at 2, I could begin the loop at 3. They were basically going around the loop once, but the vertices in which they were beginning were different. So that I want to be able to cover all of them here. So that's the reason why I repeat this loop here. Please note that this is a test path. So that need not satisfy the notion of a simple path or a prime path because it's just an ordinary test path. The only condition that it has to satisfy is it has to begin at an initial node, which is 0 for our example, and end at a final node, which is 6 for our example. In between nodes can be repeated because it's not a test requirement for prime path coverage. It's only a test path for prime path coverage. So test paths need not be simple cycles. They need not be maximal simple paths. Right? So if I do that, then right there I have toured 4 prime paths in this list. I have done this, I have done this loop. Right? So I've entered the loop from the initial state and I have gone through the loop. So what I do is the remaining. What is the remaining amongst the remaining prime paths, which is the longest prime path that is left out? That is this 0, 1, 5, 6. It so happens that already begins in an initial node and ends in a final node. So it doesn't have to be extended anymore. So I leave it, right? What is the other path that is left out? Those are these 2. In this path 0, 4, 6 again begins in the initial node and ends in the final node. But I need to be able to give scope to cover this loop. So I extended it to 0, 4, 4, 6. So putting it all together, the complete set of test paths for prime path coverage as my test requirement are these lists that I obtained. If you remember, I took this, which is the longest prime path. I extended it to cover the loop over the vertices 1, 2, and 3. Then I took the path that skipped the loop. Then there was one more loop which these 2 test paths cover. right? If you notice and if you worry about is this the best set of test paths that I can get for prime path coverage for this graph, I would say no. Why? Because if you see, the simple reason the 0, 1, 2, 3, 1, 5, 6 is completely embedded within this second path, right? So I could remove one of them, right? So I've not got the least number of test paths that I could cover. Similarly, 0, 4, 6 is completely embedded in 0, 4, 4, 6. So I could remove 0, 4, 6, right? But that's all right. The focus for us is not to get the most optimal set of test paths. The focus for us is to be able to correctly define the test requirement and get a set of test paths that satisfy the test requirement. That's what we've done here, right? So, in general, the problem of what is optimality, optimal test path corresponding to a test requirement, there are several notions of optimality available in the literature. We won't really focus on that because I want to be able to move on, but I'll point you to good references where you could look up for this kind of information, right? In general, many algorithms that come up with optimal test paths or decide what is an optimal notion are typically intractable problems. A lot of them are NP complete problems. In fact, there are what we saw was explicit state algorithms, algorithms that use breadth first search or depth first search. You could leave them aside and do what is called symbolic execution based algorithms. I will do symbolic execution a little later in the course after a few weeks. They also can be used to obtain specified path coverage criteria. I would like to end this module by encouraging you to use this web app. So the textbook that I've been using for this course is the book by Amman and Ofut called Software Testing. In the web page of the textbook, they have a very nice web app for several different coverage criteria that they introduce in the textbook. For now, you begin by using this particular web app, the app that is available in this URL. You can try out how the various structural coverage criteria work by inputting your own graph, and then they have algorithms, which are basically Java programs that they have written, which will output the test requirement and the test paths that satisfy the test requirement, right? If you want to go ahead and read further on, this paper is a very good reference to talk about prime path coverage, which is the most difficult structural coverage criteria that we saw till now, right? Thank you.